Welcome back, everybody. Today's lesson is on apparent motions, how things appear to move, not actually how they move. And we're going to be looking at the sun, the moon, planets, the stars. What a beautiful shot here to start things out with. This is the apparent motion of the sun from east to west, and this is taken in Italy. We are looking towards the south in this picture because that's where the sun is the highest in the northern hemisphere at noon. And it's been photoshopped together, stitched together, so you can see all these different shots, maybe one an hour or one every half hour or so. So great shot here. All right, apparent motions of celestial objects. Now remember, celestial objects, any object outside the Earth's atmosphere. So because of the Earth's rotation, because of our spin, all these objects appear to move. Now let's focus first in on the stars. The stars appear to move east to west in an arc-shaped path at 15 degrees per hour. And star trails will show us evidence of that, in fact, evidence of our Earth's rotation. And you can see in these photographs here, these are star trails taken with a camera whose shutter has been open for a long period of time. And you can actually tell how long a period of time these things were taken for. First, let's just focus in. You can see this. Let's look on this side. This star trail right here. That right there is one star, and the light from that star is kind of smeared across an arc in the sky as the camera shutter was open. So if we were to measure this, we could actually figure out how many hours the camera took this picture for. And you know, let's say we measured it and it was 45 degrees. So 45 degrees, and the Earth rotates 15 degrees per hour, you could divide 45 by 15, and you get a 3-hour photograph. Now, if it was like 60 degrees, it'd be a 4-hour photograph. If it was only 30-degree arc, it'd be a 2-hour photograph. 15 degrees for an arc, it'd be only 1 hour open. And it's probably somewhere in between all those anyways. But you get the idea. That's how you calculate that. Now, one of the questions I had thrown up here, but it just disappeared on me, is what must be at the center? What's that star right there, that bright smear right there at the center of these two photographs? And remember that everything seems to be going around it. So if you're thinking, hey, that must be the North Star, you're right. That's Polaris. And it's the same thing over here too, Polaris. So it's pretty cool to see a picture like this. All right, now if we were to look at stars and how they move through the sky facing different directions, here's how it would appear. So first, looking east. Looking east, at least in this part of New York State, Fort Plain, in the northern hemisphere, stars are going to move up and to the right at an angle. Looking west, they set down and to the right at this angle. So that's how the stars would appear if you're kind of looking one way, east, and then you spin around 180 degrees and look west. If you look north, however, remember the photographs on the last slide, you're going to see star trails. Those star trails are going to be curving around in this direction. And if we spin around 180 from north to south, you'd see stars rising in the east, setting in the west, moving in this big arc-shaped path. So that's how stars appear looking south. So east, west, north, and south. Just be aware that you might be asked to answer one of these different directions or more than one. Okay, next thing we got to do. So we just drew the star trails above. Let's cross that off. Now we have to go to the diagram below and let's label the zenith. Zenith is the point straight above the observer. So this is the zenith up here. All right, got that done. The direction to Polaris. Polaris, the North Star, it's in the north sky. So if we're here in Fort Plain, I'm going to draw an angle up, about that angle or so. And Polaris. You guys remember we're on this lab right now. Most of you are on this lab right now. And that represents that metal bar that we have through the hole in the plastic hemisphere. That's towards Polaris. And let's cross that off. Circumpolar stars, those are those stars in the star trail photographs you looked at. They would be going around, or appear to going around, that center Polaris star. So something like this. Okay. And then any 3 star trails. So I'm going to pick a star trail that goes directly due east to due west, just for fun. Let's do that. So it looks something like this. Dash on the back side, solid on the front side. So there's one star trail. Perhaps there was a star that was a lot lower in the sky. It'd do something like this. And perhaps one that is in between those two. Something like that. And so you get an idea that stars are moving along these paths because the Earth is spinning. And we are done with this page. Okay, moving on. Now the planets also appear to move east to west in an arc-shaped path at 15 degrees per hour. Remember the Earth's rotational rate, 15 degrees per hour. But planets do something else over longer periods of time, over weeks and months. Planets appear to drift backwards, then forwards again. They appear to wander, and that's what planetheos means, where we got the name planet from, the wanderer. And so in this diagram here, you can see there's Earth moving from positions 1, 2, 3, 4, and so on. And you can also see Mars moving in positions 1, 2, 3, and so on. Mars doesn't move as far between those positions, which are the same amount of time length between them, because Mars is in a farther orbit away from us. So we're going to catch up to Mars. And that's exactly what's going on here to make the planet Mars appear to go backwards. So first, if we were to look from Earth at Mars at position 1, we would see Mars in the sky like that. Now behind it would be all these stars. These stars are light years away, so far away that they don't appear to move, comparatively speaking, to the planets. They're like the background field. And as Earth starts to come around here, you can see Mars appears to move to the left. It wanders compared to the other stars behind it. But as Earth starts to catch up to Mars, Mars stops going to the left. And at position 5, it's going to the right some more. Position 6, it's moving to the right some more. And then at position 7, Mars appears to move back to the left again. And then 8, it's moving back to the left even more. 9, so on and so forth. So you see this long snaking path of Mars over many weeks through the sky. And that's how planets got their name. They wander. And you know, the ancients didn't really understand what was going on here. They thought the planets must be special because they had a mind of their own, if you want to think of it that way. And that's perhaps why they named them after gods. So we kind of already answered these. Let's move right on. Okay, the sun. The sun appears to also move east to west in an arc-shaped path at 15 degrees per hour. So that's the theme for today, this east to west arc-shaped path, 15 degrees per hour. Now the sun, we can draw some paths for this. This is just for practice, then you guys are going to draw some on the next slide. But let's start out with December 21st, first day of winter. Now one thing we know about first day of winter, it's a short day. The sun rises in the southeast, sets in the southwest. So I'm going to do my best to draw this, something like that. And that would be December 21. And we know that on the equinoxes, which are March 21st or 20th, September 22nd or 23rd, that's where the sun rises due east and sets due west. So we're going to do my best to draw that. These aren't pretty sometimes. And I'm just going to put the word equinoxes here so we don't have to write both dates down. And for June 21st, this is our longest day of the year. Now here's where the sun's going to rise in the northeast and set in the northwest. So here, it's going to come up, not straight overhead, not here. You have to be at the Tropic of Cancer or between the tropics to get that to happen. But you can see the sun is highest there compared to the equinoxes in winter. And you notice the sun is rising in the northeast and setting in the northwest. And equinoxes, it's rising due east, setting due west. In winter, it's rising southeast and setting over here in the southwest. Some other things we could label: Polaris. Polaris would be off to the north Now in the north is over here, so we're going to draw this about there. And remember that our latitude equals the altitude of Polaris. So since we're about 43 degrees north, just imagine that being about a 43-degree angle. I'm not saying it's accurate because I'm just winging this thing, but you get the idea. We were measuring this in lab class right now. And then zenith. Zenith is always the point directly above the observer, so straight up 90 degrees. The sun never reaches zenith, even on the first day of summer in this part of New York State. So we got everything checked off. Let's go on to the next thing. Okay, now this little applet here, if you're watching this on YouTube, I'm going to skip over this, and we'll play around with this in class, you know, probably the beginning of the next class as a review. But it's a great applet to show you the path of the sun. All right, so now we're going to kind of sum up that last set of diagrams we just drew, just in separate pictures here. So first let's start with March 20th and September 23rd. And south is on the left, north is on the right. Got to check those things. So the sun's going to rise in the east, move in the south sky, and set in the west. And due east and due west for the equinoxes. And there's the sun at noon. I like to draw that on there, all my pictures. Okay, for June 21st, remember everything slides to the right. Sun's going to rise in the northeast, move higher in the sky, and set in the northwest. There's the sun at noon. And then for December 21st, that's when the shortest path of the sun is observed, and it's going to rise in the southeast, set in the southwest. There's the sun at noon. So you have to be able to draw these pictures and interpret them, and also to realize that if you see the sun getting higher in the sky day after day after day, you must be somewhere between December 21st and June 21st. December 21st to June 21st. However, if instead you see the sun getting lower in the sky every day at the same time, usually we measure this at noon, solar noon, then you must be at this point where it's getting lower after June 21st, moving towards December 21st. So everything just flip-flops here. And you know, the ancients had all different kinds of ways to measure the sun's path and the angle of the sun, mainly for determining, you know, all kinds of things like planting seasons and holidays. Now in this last picture, you see the north is on the right in all these and south is on the left, but turnabout's fair play. I could place north on the left and south on the right, or we could turn it any other way. So you just have to be aware, be smart, and look at where the compass directions are. So in this particular case, you can see noon on June 21st. It's rising in the northeast, setting in the northwest, but everything's kind of on the opposite sides now. And same thing with the equinoxes and December 21st, but the sun's rising and setting points are shifting. What if you were asked a question, what place on Earth could this be? And you knew that the sun was at zenith on the 21st of June. There's only one latitude on Earth this place could be at, and we learned that there's only one line on the Earth. The Earth, actually I should draw it with a little bit of a tilt in this case. The equator, and you know that one's Cancer and that's Capricorn. The first day of summer, the Earth is tilted towards the sun the most in the northern hemisphere, and that means that this must be at 23.5 degrees north, or the Tropic of Cancer, somewhere on that latitude line. All right, here's a question. What's one of the two possible dates for the sun's path shown below? And we can see here it's rising due east, setting due west, so we know it's got to be an equinox. Has to be. What would the path look like for June 21st? Well, it's going to be shifting. But remember, we're now in this reverse turnabout type diagram, so everything's going to be moving this way. So that would be like June 21st. And December 21st would just be shifting and rising in the southeast, setting in the southwest. And you get better at this the more you do these things, which once again is what that lab's all about. But it does take some practice. Oh, another question. Which one of these three sun's paths would produce the shortest shadow of the observer there? And if you said June, you'd be right. June would make the shortest shadow because the sun's the highest. The longest shadows would be produced in December because the sun would be shining at a lower angle and produce a longer shadow than all the rest. All right, hopefully you guys learned something about apparent motions, and I'll see you next time.